I was given the title, It's a Small World. If I would look at the glacier map of the world, with more people moving into cities, cities are getting bigger all the time, I would like then to ask the question, how can we map out the interactions between these cities? Not only cities as islands, but these islands are somehow connected. And I would like to ask in particular the question, are these types of connections changing if the world is indeed getting more and more a digital world in which distance frictions play increasingly a lower role? So that's in fact the question I have. And in the current literature there is an enormous debate. Let me start on two extreme sides. First, the work of Thomas Friedman, for instance, with his book on the world is flat. In a digital world, we have access to everything. It doesn't matter whether you outsource your business to India or to Bangladesh. The world is flat, activities can take place all over. That might have implications for urbanization, because why should you move into cities? Others, like Phil McKinn, Anders Rodriguez-Posse and others, have just argued the opposite. The world is getting more and more spiky all the time. We get more and more inequalities. In fact, that's also Friend's argument. You get more inequalities rather than a flat world. So what is the truth? What I would like to do today is to go back to one of the founding fathers of modern physics, Isaac Newton, and listen carefully to what he has said about interactions in physical space, but economists and social scientists can learn a lot from physicists. Second, I would like to confront some of his departures with some wisdom by Waldo Tobler, one of the traditional, well-known American geographers. And I would like to confront these two views, and then again, based on the existence of a digital world, try to find out, also based on some simple modeling experiments, who is right. So this is where we are. That doesn't work, I'll just use this one. Okay, good. So there are a couple of dilemmas I would like to discuss with you. First, there is what is called the gravitational principle, the universal gravitational principle, that's Newtonian wisdom, versus digital connectivity in our virtual world. Now what we see is all kinds of new trends which have been mapped out in many publications, like online services, electronic orders, business services, and virtual realities, etc. The dilemma which next comes up then is the dilemma of what is sometimes called the death of distance. If that were true, it might imply that some of the foundations of modern regional economics, as advocated by von Thunen, are no longer valid. We might lose our orientation point, and it might also imply that perhaps trade and the principles of trade and modeling trade might have to be done totally different. It might even lead to what some people have called a requiem for Hermes. Hermes is the Greek god of trade. So we really are faced here with a series of very important challenges. Here I give the controversy between the two thinkers. Let me begin with Isaac Newton. Isaac Newton, more than 300 years ago, invented his universal principle of gravitation. Mind you, that was not a simple law which he had invented overnight. Historically, if you read what has happened, it was almost devastating to him. As a rather young person, he was a fellow of the Royal Academy, Royal Society in London. and he was a physicist. By then the world was governed by mathematicians more than physicists, because physicists were half scientists and half speculators, etc. So he presented his universal gravitation principle. And halfway he was interrupted by his fellow mathematicians. And they were laughing, loudly laughing at him. That is totally wrong. And he became furious and had a big argument. At the end he left the room. For 3 years he didn't return to the Royal Society. He was offended because the mathematicians had told him it was wrong, it was mathematically wrong. And later on he realized it was wrong. And then he wanted to take revenge. And he said, I will come back, but with a better model. And it took him 3 years to find out the mathematics of his model. And then he came back. After 3 years at the end, yes. Then the model was correct. And then gradually it was accepted. But the entry of this universal principle was problematic. But what he said essentially is, if you talk about matter, then without the mediation, that's here the literal translation, the mediation of something else which is not material, then this matter should operate upon and affect other matter without mutual contact. And then he said, gravity must be caused by an agent acting constantly according to certain laws. There must be a law. Why? If you have mass 1, you have mass 2, why there is interaction and why there are differences in terms of interactions, even when the masses would be equal. And then, of course, it is distance, or in fact, 1 divided by distance squared. So these are the principles. And then he could prove that this would hold true in physics, and that has been with us for centuries. And it's still, despite many amendments, etc., but it's still with us. Now we make an enormous jump. 45 years ago, Waldo Tobler from Santa Barbara, not by then Santa Barbara, nowadays he is still in Santa Barbara, in his work on the decline of Detroit, he formulated in passing another law, which later on was called the first law in geography. Geography doesn't have much laws, because what is the theory of space? That's a difficult question. But he formulated the first law, and he said everything is related to everything else, but near things are more related than distant things. You would say, how naive, so simple. How can a decent geographer formulate such a simplified law? It's in fact just Newtonian, a rephrasing of Newton. But be careful. Newton, now it comes, was talking about matter, particles, whatever, in physics and astronomy. Tobler did not talk about matter. Tobler was talking about everything. Everything. That's the whole world. Everything. It's matter, it's a table, it can be anything, it can be this stick, it can be water, but also ideas, thoughts, data. And therefore, Tobler might be more relevant for a digital world than Newton. And the question is Newton valid for our digital, emerging digital world, or is Newton in the meantime completely outdated and should we believe Tobler? So that's an interesting question. Now the history of the Newtonian philosophy in the social sciences is very interesting, and I just very quickly give you a few highlights. Already more than 150 years ago, Carré published a small book on the principles of social science. It was not on economics, more on social science, interaction among people. And then he said, okay, if you have more people here, more people there, and there's some distance correction, of course, they interact more. But it was a simple application of, let's say, Newtonian physics. Then later on, Ravenstein, he did the first empirical assessment of migration flows, which he called the laws of migration. And it was just purely Newtonian philosophy. There's a point of origin here, there's a point of destination there are migration flows, and the flows of migration are proportional to the size of these 2 points, A and B, origin, destination, and of course to be corrected for distance. Then later on, that's interesting, a Polish economic geographer, Janowski, published a booklet which in fact highlighted some of all these principles. And he had also a physical background, so it was very interesting. Unfortunately, it was written in Polish, and until 3 years ago, no one knew about it. It was only in Polish, and during the war it was half destroyed, etc. 3 years ago, that was found in somewhere in the dust in the library of the University of Poznan. Then it has been translated, and since 1.5 years, there's a small booklet written by Janowski. You can get it, very simple. Very interesting, highlighting comments on the principle of gravitation for social and economic interaction, on trade, on communication among people. And it's a pity that this got lost under the dust of a library. Then later on, after the war, Walter Isert, in his book on methods, in fact highlighted and also emphasized the importance of Newtonian philosophy. Later on, the first Nobel laureate in economics, Tinbergen, and his disciple Hans Linnemann, they applied the gravity model to various questions on trade, transport, migration worldwide, etc., which had to do with Tinbergen's philosophy on the new world, etc., and equality and inequality in our world. Mind you, Tinbergen was not an economist. He got the Nobel Prize in economics, but he was a physicist, so for him it was very easy to apply the principles of Newtonian physics to economics. In the same spirit, later on, Bill Alonso, also mentioned by Glacier before, he developed his general theory of movement, in which he took the Newtonian philosophy, but he said the marginal totals from A to B and all the volume, the marginal totals can also be endogenous, so they can be explained as in an interactive process, which makes the model excessively complicated. And only recently, just a few months ago, this whole complex mathematical problem has been solved, which is a very complex thing if you make the marginal totals endogenous, because this is a double nested nonlinear model. At the same time, and slightly later, also another person was talking about similar things, Alan Wilson. And he formulated the entropy principle as the basis for spatial interaction models, flows from A to B to C, etc. Mind you, Wilson was not an economist, nor a geographer. He was a nuclear physicist. Again, many of these ideas came from physics, because they could easily understand Newton. Then, slightly later again, we got a class of what is nowadays called discrete choice models, then McFadden and Kahneman. McFadden economist, Kahneman in fact from psychology, again an impact from another type of discipline, but dealing essentially in their flow analysis with similar types of models as the previous classes. At some stage, together with my colleague Auregiani from Bologna, we have been working on all these classes, trying to get some sort of a uniform perspective. And we have tried to work on it and to prove that whether you have a discrete choice models, which is more rooted in psychology and microeconomics, or whether you have an entropy model, or whether you have a gravity model, it all boils down to the same behavioral economic equivalence. So whatever you do, at the end, the economic foundation in terms of a one-to-one mapping, the one model into the other one, is more or less identical. So economists should not feel shy to apply gravity theory or entropy models, because they can always be interpreted as being rooted in economic, microeconomic theory. At a later stage, also Paul Krugman has been working on this in his new economic geography, in which in fact he reconciled two elements. On the one hand, the agglomeration principle. These are the masses in the Newtonian sense, bigger and smaller, and the scale advantages in urban agglomerations, and the distance friction costs, which in fact he interpreted in terms of trade and migration flows, etc. So it was in fact some sort of an integration of the different aspects. So far so good, and we could understand the world, and we were living in a comfort zone because we could more or less model this whole process. until by the end of the last century, Cairncross suddenly came up with something which he called the death of distance. And this has created enormous interest, headlines in The Economist and so on, worldwide. If there is a death of distance in a digital world, the whole Newtonian world breaks down, because you only have two masses and there is no distance friction anymore. Then the model doesn't work anymore, and then you get these principles of a flat world, which is in fact a hypothesis to be tested. So the question then is, if we move from a Newtonian physical world into a digital world, can we use the same principles? Or is our world completely changing? And do we need totally different paradigms? Because none of our predictive models might hold perhaps in the digital world. So that's in fact where we have tried to work a little bit also on the economics and the spatial econometrics of this new world. The background of this new world essentially comes both from geography and again from physics, less from economics. There's the first contribution, perhaps in a more general sense, from sociology, which is Emmanuel Castells, also well known in KTH, of course, as one of the honorary doctorates. In geography, especially the work of Michael Betti, where he makes a distinction between cyberplace and cyberspace. Cyberspace is the world, this virtual world all over, where everything is floating around. We cannot observe it, we don't know it, but somehow it is reflected, projected on the real world. That's the cyberplace. So there's the distinction between space, which is largely unobservable, and place, where we can observe the real phenomena, even when they are the result of cyber connections. So that, I think, is an interesting distinction, which has prompted enormous volume of research on internet geography and cyber geography, etc., and on the principles of, for instance, what is the internet, what are the economic and social backgrounds, and what are the implications for our real world. I'll just go a little bit quickly, given the time. Many publications, starting beginning of this century up to, well, very recently. It's very interesting to see that if you just scan a little bit the literature, the first interest was mainly in the US, it's very interesting, and later on Europe. Europe was always lagging behind a couple of years, but in the meantime it has led also to an enormous rise in the literature in Europe. And that has prompted worldwide in the meantime lots of research in different disciplines, including economics, on cyber networks. What does it mean? What are the principles? What are the profiles? And can we identify patterns in such an unobservable and rather complex, non-linear dynamic world? An important contribution in this respect has been provided by Barabasi with his new science of networks. And he is still advocating in many articles in Science and Nature his new science of networks, where he looks into the complexity of these massive volumes of flows and sometimes information as far as you can observe them. Just a simple example here, Twitter languages in London, different colors, different languages. If you have a tweet, you can identify, if you have the information, you can identify the language. And then you know a lot, because you can identify what kind of language is the tweet, and then you can find where was it sent off from. And that's important, because for security services, if you are looking for terrorists, and if you might assume that perhaps certain terrorists would use Arab as a language, then you can easily find out where you should concentrate your efforts. So this type of information is excessively important for modern security services and so on. So this is permanently being used. Of course, it's very often privacy-sensitive information, but the general pattern, of course, is different. Now the question is, if you have this, is this some sort of a spaghetti model? You say, well, it's random and we have no idea. Well, if you carefully look into it, there might be patterns. And if you have the patterns, of course, then you can identify the structure, and out of the structure you might say, well, there's a certain theoretical framing of why the patterns have emerged. We can observe them. And that is one of the interesting modern things. And there are two types of directions there to identify these elements. On the one hand, you might say, well, we have a pattern. We do some of a statistical analysis on small and scale-free networks. We can identify where there's a hierarchical composition of different flows. We can identify the structure, and then statistically at least, we know there is a regularity. It's not random. Or you might say, we can try to explain it. That's a different thing. That's more what the economists would like to do. They would like to explain the world based on behavioral paradigms, etc. And I will just quickly go through it. On the one hand, doing the statistical analysis, on the other hand, doing the explanatory analysis. The statistical side, here we were lucky enough to get a lot of data on internet flows based on IP addresses all over the world, including Europe, including China, including transatlantic flows, etc. There are not that many of these data, but we were lucky to get these data out of the Dimus project from a few years back. And here you see some of the European patterns. If you look at these patterns, they tell us already something. Because if the world would be flat, why should there be a certain concentration here among major centers? It suggests almost there is some sort of Newtonian pattern, even when it is cyberspace and distance does not play a role. And we have to correct for this, and we have to look into the question, is there an identifiable pattern, and how can it be explained? So that's the main question. The patterns can be identified just by looking into what is called the Nodes degree distribution. If there is a straight line, etc., you can use the different curves with an exponential law, power laws, etc. And if you get this type of pattern, then you can see there is some sort of a hierarchical structure and composition. And here I give a little bit of the statistics, and in view of the time, because Hans warns me, I only have 4 minutes left. Then I go to the next step. So there is a pattern, that's true. But then, of course, what is the explanation of that pattern? That's the economist question. And the economist question then would look into the question, can we deal with a straightforward Newtonian model? An internet flow or a whatever digital flow from A to B is masses A and B corrected for distance, or don't we need distance, or do we need other things? That's where I would like to introduce a little bit the theory of proximity, which has become rather fashionable in the past years, where instead of distance, the reverse measure of proximity is being used. And proximity then has a set of meanings, not only physical proximity, like IP addresses and geography, but there can also be different types of relational proximities. And in the, what is called nowadays sometimes the French school, work of André Torre and others, various types of proximity have been distinguished. Not only the physical proximity, distance, but also cognitive proximity, organizational proximity, institutional proximity, population, whatever type of proximity. There's a whole categorization of proximity measures. Also in a recent article we have published in the Annals of Legal Science, we have tried to map all these out and to measure them. And for this specific application, which I showed to you, the internet flows worldwide, we use different types of proximities. Now, I'm not going to too much into all the details of the model, but here you have the internet flows, IP, from I to J. So that's just a flow. Here you have the Newtonian distance or masses, how many IPs in the one place, origin, destination. Here you have a time correction. And here you get, this is typical Newtonian, the distance. And here you get all the other kinds of proximity indicators. So what we try to do is to find out whether Newton in itself is valid, whether an extended Newton model, which would map out the connections between different cities, might be valid, looking into different types of proximity. So proximity is the additional element to a Newtonian model. And then we do successively all the steps, and I'm not going to, because it's a rather technical econometric analysis, so we did stepwise, going through all these things, and I just come up here with the final results. It turns out that the purely Newtonian model for cyberspace has only a limited relevance. Then if you add it stepwise and complement it with different types of proximity indicators, technological, organizational, etc., then you come to the important conclusion that this thing, which is Tobler's first law of geography, that this is true in an analysis of the connections between cyberplaces. So essentially, and there are a few more things on board, and localization effects and cost effects, but essentially what we have found out here is that Newton, in a way, is not totally outdated, but if you extend Newton with proximity effects, which are more everything, ideas, cognitive elements, etc., if you extend Newton with more things, you get a much better fit of the model. So if you ask me then at the end, who was right? Well, Newton was certainly not wrong, but Tobler was more right than Newton for our cyberspace. So that's my conclusion. Thank you very much.